Blaise Agueray y Arcas is the last one who is talking about AI in general. He is now the vice president of Google Research, and I also have the pleasure to say that he has just finished writing a book. This might be of interest, so if anyone wants to read what he has to say about many other things as well. The topic of his talk today is: what can general AI teach us about the nature of intelligence? So, Blaise.
Okay, so I'll talk about the brain as a prediction machine today. So I think you've already given a very nice introduction, so I won't waste folks' time with saying much more about myself. I until very recently was running a fairly sizable part of Google Research, and now sort of in a more I don't know how to put it, in a more CTO-ish sort of role with technology and society and Google Research as well. I've also done a fair amount of writing, as you mentioned. Some of the more relevant writing for this talk is probably a series of essays in Noema and in The Economist and so on about the role of large language models in intelligence and whether or not they are actually intelligent. I guess, spoiler alert, I think they really are intelligent, not just a simulacrum of intelligence. And I know this is a somewhat controversial position. But that's what I'd like to begin by talking about, sort of my perspective on artificial general intelligence and why I've come to believe this. And a few words about the politics of the response to the kind of AI moment that we're in, which I've been finding very interesting just from a human perspective. And then I hope to spend most of the talk delving a little bit more deeply into the question of what intelligence actually is and what we might gain by taking seriously the idea that prediction is the core of what we mean by intelligence at every scale, whether that's human beings or bacteria, or maybe even things simpler than bacteria, and give a bit of an evolutionary perspective on this. So last month in October, Peter Norvig and I wrote an essay in Noema called "Artificial General Intelligence is Already Here." We wrote it because we found ourselves in a conversation at some point, wondering to each other why it seemed like everybody was saying, we don't know whether AGI, whether artificial general intelligence will ever arise, whether it's only a decade off, or maybe it's 50 years off, now of all times. It just seemed like a real surprise, because speaking for myself, when I learned the meaning of artificial general intelligence many years ago, as compared with artificial narrow intelligence, my understanding of that distinction was that artificial narrow intelligence was the kind of things that we had last decade. If it's a speech recognition system or handwriting recognition or an image classifier like ImageNet, these are neural models in many cases designed to do specific narrow tasks. If it was a model trained to play chess, you couldn't have a conversation with it. If it was trained to play checkers, you couldn't turn around and say, play chess. Even if it was a chess player and you said, okay, let's now pretend that all of the pawns can move backwards as well as forwards, you had no way of doing this. And that seems to be exactly what sort of LLMs and this new unsupervised learning allows one to do to make the intelligence general. And that was, so I thought, we're here, we've arrived. Not that these models are superhuman, or artificial superintelligence or anything of the sort. They obviously vary tremendously in terms of their skill or capability depending on what you ask them to do. In some skills or in some contexts, they are in fact superhuman. In others, they are subhuman, although to even talk about super or subhuman is a little complicated because humans themselves have such a very wide range of different capabilities depending on the details of the domain and what you ask. So, when I just go on Google and ask definitions of artificial general intelligence, specifying that I only want results from earlier than 2019, you'll find results like this one. the capacity of an engineered system to display the same rough sort of general intelligence as humans, or display intelligence that is not tied to a highly specific set of tasks, or to generalize what it has learned, and so on. So by all of these historical definitions, it seems to me that that's what we've got. And that's, of course, not been the response. The general kind of cycle that I've seen in the press and among the commentariat is, oh my God, look at this new thing that AI can do. Oh wait, here's something else here's something where it does a dumb response. So, phew, there's nobody home. It's not really intelligent. AI is hype. And this is just a hype cycle. And then in 2 months, it can do the thing that people were complaining about 2 months ago, and then the cycle repeats. I was, when I was making this slide, I was especially tickled by this one, in which somebody asked GPT-4 a question with all of the letters of the words scrambled, and it understood the question, it unscrambled them. I thought this was especially interesting because it's not as if this task of unscrambling sentences that it submitted is something that it was trained to do. This is just something that somebody tried and it worked. So to me, that was, things like this are pretty strong indications of general intelligence. Even multitask learning, in which you say, well, there are a whole series of tasks, but we have to decide in advance what they are very different from this kind of stuff where we discover later on all kinds of things that it can do, and we maybe are starting to even get into the regime of you have to work pretty hard to to come up with prompts or things where it will really say something dumb. So that's my sense of where we are, that the frontier models have achieved a significant level of general intelligence according to the everyday meanings of those words, but most commenters are not admitting it. Peter and I thought about this for a little while, and our sense was that there are 4 reasons that people are hesitant to admit it. Although, to be honest, I think that more people in the general public will say it than specialists or people in AI or academics. And there are some psychological reasons for that, I think, and probably part of it is also a desire not to look stupid. Because if anybody is saying that it's fake, then if you're saying that it's not fake, you're a little bit exposing yourself, I think, intellectually. The best reason to be skeptical, I think, is skepticism about metrics for artificial general intelligence. And this question of metrics is a very complicated one, and one that's kind of in rapid turnover at the moment. Then there is what I think is a less healthy reason to be skeptical, which is an ideological commitment to alternative theories about AI or techniques about AI, without which you say it can't be real AI if it doesn't conform to some a priori theory. Then there's a devotion to human or biological exceptionalism, basically just saying, well, it can't be intelligent because only people are intelligent, or it can't be intelligent because only a biological system can be intelligent. And finally, there is displaced anxiety about economics and about other issues of human dignity and so on that I think are real. And these are important questions for us to think about, but they're questions that are probably good to address head on, as opposed to displaced anxiety, onto like, is it real or not, on the basis of things that are actually about economics or about dignity or about other questions. Now, one paper that has gotten quite a lot of attention on the metrics side of things was from May of this year. This was by Sanmi Koyejo and colleagues at Stanford, Are Emergent Abilities of Large Language Models a Mirage? I thought this was a really interesting and important paper, although its title is deceptive. My one real critique of this paper is that the title is not sort of what the paper is not what it says on the tin, as it were. So the observation that Sanmi and colleagues made is that there's been a lot of talk about emergent capabilities in large language models, and the usual way that emergence is demonstrated is by showing that as a model scales up in size, it looks like crap at some particular task until suddenly at some critical scale, this capability seems to emerge, whether that's being able to do modulo arithmetic or being able to transliterate or unscramble words or what have you. And that's, on one hand, that sort of fits with the philosophical tradition, in physics of emergence, of properties of holism that can't be inferred from the parts. It also is something that I think gave some people anxiety because they wondered, okay, well, is superintelligence an emergent capability that's going to come out magically at some point, or self-consciousness or this or that? Is it the case that we're going to kind of keep scaling up these models and suddenly something will happen, where it'll tip? And what Koyejo and colleagues noticed is that all of these emergence effects are actually functions of the nonlinearity of the metric itself. So they're not real. The nonlinearities aren't real. In other words, if you do a math evaluation, for instance, that takes into account, that gives partial credit, or that looks at shorter math problems and so on, then you see that the performance is actually quite linear. And as you shrink the model, it gets worse and worse, but there's not some point at which there's this discontinuity or knee. The discontinuity is a function of the metric. I think that's a really important result, but it doesn't mean that the emergent abilities are a mirage. It means that the emergence is a mirage. And I think there's a pretty big difference between those theses. So is there work needed on better metrics? Absolutely. But for me, the main message of this paper is kind of optimistic in the sense that it says, there aren't some mysterious things hidden in the network that might come, pop out at some magical scale, but rather that we should be working to develop metrics that are smoother and that show us how capabilities improve continuously as models scale. Now, then there are folks like Noam Chomsky and Gary Marcus and so on who put a lot of opinion essays out into the world. This one of Chomsky says, machine learning will degrade our science and debase our ethics by incorporating into our technology a fundamentally flawed conception of language and knowledge. We know from the science of linguistics and the philosophy of knowledge that LLMs differ profoundly from how humans reason and use language. These differences place significant limitations on what these programs can do, encoding them with ineradicable defects. I have a problem with critiques like this one, which is that they are not based on the success of any alternative method. And so in that sense, they're purely ideological. If we want to look at things that a model cannot yet do and say, intelligence, I won't be satisfied about intelligence until this task or this set of metrics is satisfied, this is entirely legitimate. If one says, intelligence cannot be achieved through those methods, but through some other methods, even though these other methods haven't shown any progress at making real AI systems, then I think we're not really in the realm of science. And that's the problem that I have with critiques like this one. And there are people doing good work on metrics, and anybody who is finding things that current generation of models don't do well is doing good work, is doing a service to the field. And what we've found is that as that frontier advances, the models have been quite rapidly overtaking those new frontiers, and we keep moving the goalposts, which is good. That's how progress happens. The other critique, the more sort of the other kind of ideological critique is well characterized by this neo-Luddite reading group. This really is a thing. Victor Gomez's website is the screenshot that I've taken here, and he actually has a couple of my essays on the neo-Luddite reading group, which is an honor. But this is a Marxist take on opposition to AI because it takes the form of capital versus labor and so on. Conversations worth having. Is capitalism durable? Should we be thinking about different ways of organizing ourselves? I think these are really good conversations to have, but they're not fundamentally conversations about whether LLMs are actually intelligent or not. They're more about what we should do about it and how we should organize ourselves in response. So anyway, enough about the sociological side of this. I'd like to switch into a more technical mode. So. All of this brouhaha has really ensued from the great success of transformers over the last several years. But my sense is that the details of the model are actually not really the relevant thing. I'm sure that transformers will continue to evolve and that the model du jour will look different in a few years' time. But there are a few things that happened that really changed the game from, say, 2018 or 2019 to now. One of them is autoregression, meaning that these are all sequence predictors that use the past, the sequence of tokens in the past, to predict the next token. And that's very different from, say, convolutional neural nets or something that will take an image and then spit out a label. The second is the use of language and the focus on language as a modality in which that autoregression takes place. This is important, I think, because language has evolved for very specific reasons among humans, including the ability to teach and to learn, and in some ways to act as a superorganism. And so it's quite, with the fact that we began to see all of these extraordinary capabilities start to emerge when we began doing autoregressive training on language, I think is not a coincidence, and there's at least one way of understanding that or interpreting that in saying, well, intelligence is in some sense a very collective endeavor. It's about humanity as a whole. It's not really just about our individual brains. And the moment we start to link other predictors into that same graph, that same social graph, it's really the same intelligence that they are tapping into. It is us, for a greater value of us, if you like, than just thinking about us individually. And finally, scale. As these models get bigger and bigger, even though there's not some magical emergence, our own metrics, our own internal subjective metrics of intelligence have a lot of those same kinds of needs that some of the formal metrics have, and therefore things that weren't that impressive suddenly become very impressive just when the model gets big enough. So the state of play back in 2013 was that neural nets were finally cracking visual perception. We had AlexNet and successors, but this was all strictly narrow AI. There was no debate about AGI glimmers, and progress in natural language processing dramatically lagged progress in vision. It's not like we weren't trying to do next word prediction. In fact, in my own group at Google, we were working on next word predictors for the Android keyboard, because that's the one you use that suggests next words on the top of the keyboard to speed up typing. But we knew that next word prediction on Android was always going to suck. We knew it would suck because we understood that next word prediction was AI complete. Meaning, if the previous word was Humpty, the next word is probably Dumpty. If it was Hocus, it's going to be Pocus. But if the previous words were all about a long math problem, and the next word is the answer to the math problem, then you need to actually do the math problem in order to give the next word. Or if it's a long story, and the sentence is at this point Jen was feeling rather. Then in order to fill in the next word, you have to have theory of mind. I mean, there's kind of no end to the number of things that you have to have in the generic case in order to do next word prediction. So we knew that since there was no way that mere next word prediction could actually solve AI, if just approaching it in some crude statistical way, there was no way we'd be able to, to get beyond a certain ceiling. At least that was what we thought. Now, we did know that as these models got bigger, they got better, but we assumed that there was an asymptote and that it would never get up anywhere close to the hard cases. But what happened with transformers and very large models was that simply trying to do next word prediction at large scale with a big enough model appeared to have actually solved AI. And that was a big surprise to me, and I think to a lot of other people as well. Knowing that it was AI complete, we imagined that there would have to be some magical ingredient that would have to be put in order to, get above that threshold, and we just surpassed that threshold by making the model bigger and bigger. And with the simple trick of attention, of being able to, to look at the entire past set of tokens rather than having some more predefined memory, as with an LSTM or something like this. So that was a real surprise, but maybe in retrospect, not as unexpected, or shouldn't have been as unexpected as it was, because there have been theories for a long time, and this is why I asked the question about pain. There have been theories for a long time that the brain is fundamentally about prediction of the next token. Friston's active inference hypothesis, going back to 2006 or so, earlier models even about predictive processing, and in some sense these go back to Helmholtz or even earlier. Are all predicated on the idea that the reason we have brains is to predict the future given the past, and so maybe that's all it is. Maybe that's what we are. We're predictors of the future given the past in an autoregressive setting where that future includes actions that we take. And that's a big part of the trick. It's not just, you're not just outside the system, it's a dynamical setting in which the tokens include everything that you've experienced and everything that you do, and the way that what you do affects your environment. Your environment also involves others, and so you have to be modeling others and modeling yourself right? And so there's a bit of a strange loop, as Douglas Hofstadter would put it, sort of quality to next token prediction when you begin to realize that the string of tokens that you're talking about is, the world including yourself, if that makes sense. So, the working hypothesis that I began to sort of think about is, let's suppose that it is just next token prediction. What does that mean? And just to give you a sense of why unsupervised, contrastive learning with next token prediction works, I just picked a random paragraph from Wikipedia. It's completely arbitrary, and I'm just asking you to imagine what it would take to fill in any given blank, right? If we were to blank out any given word in this, if you blanked out stratovolcano, then you have to know, what Mount Melbourne is, and it's general knowledge. If you blanked out the number of kilometers, then, filling that in would require either knowing the answer or being able to do the math of, how the miles convert to kilometers. If you blanked out, cone, that would involve being able to reason about geometry. So, just the fact that so much is involved in doing next sequence prediction, again, you learn a model under sufficient constraints of compactness of the latent space. You're going to build models for all of this. Essentially, you'll have a world model that includes, for every practical purpose, all of these concepts. So, that sort of compression constraint led Ted Chiang to sort of disparage large language models as just a blurry JPEG of the web. I think that's kind of true, but this might understate the importance of compression. Compression really is also all about sequence prediction, even though we don't usually think about it that way. The very first compressor was the differential pulse code modulation technique invented by Cutler and patented in the early 1950s, which really just involves predicting the next sample in an audio wave, for instance, using a zero or hold kind of model, so the simplest possible sort of model. And the compressed stream is the delta, or the difference, between the prediction and the next measured signal. And so you have a version of that model on the encoder side, and you have a version of the model on the decoder side, and all you need to send is the error signal in order to make the decoded stream consistent with the prediction. Now, that's a really trivial model with a context window size of 1, if you like. But as you grow the context window and as you make the model more sophisticated, compression is basically exactly what we're talking about. Compression and prediction are the same task. We're really just talking about predicting the future given the past, where the time series includes itself. When we talk about large language models, we think about this largely in the context of chatbots, where everything happens in discrete turns. But remember that if you're thinking about this in a more continuous dynamical setting, these same ideas are now being applied in robotics and in continuous signals. Continuous sound is actually a case that we made in my team. I think this is a little bit less surprising now that ChatGPT has come out with audio as well. But I was kind of showing this stuff off, and I guess it was more impressive a few months ago. These examples in which my teammates would say a couple of words, and then the model would continue, predicting their conversation in pure audio with turn taking and so on. I won't bother to play it because I think by now we all know that this works. This is increasingly working in a robotics setting as well, where robots are able to do manipulations and so on. It's the same thing. It's just prediction of the next token. Prediction also means that disambiguating co-reference, things like this classic problem of what does it refer to when I say I dropped the bowling ball on the bottle and it broke. It's just a prediction problem to understand which it that refers to, or if it's and I should point out that even language translation trained the old-fashioned way understands a lot of these same kinds of regularities. If you do these sorts of co-referent disambiguation things, this is an example of translation from English into Spanish. I dropped the guitar on the cinder block and looked down to discover that it was damaged. When you translate that into Spanish, dañada or dañado have to agree. The gender of that word has to agree with the noun, and so it has to actually understand whether it's the guitar or the cinder block that got damaged during this process. It involves actual physical reasoning. And that turns out that was actually in those old-fashioned neural translation models already, back in 2016. So they had a kind of general intelligence in them as well. We just never bothered to run them in a general next token prediction sort of way. The kind of supervised learning that we used to do in the 2010s really is, if you like, approximating a function. F of x gives y, or p of y given x. And what we're doing nowadays is just learning in an unsupervised way p of x comma y, which is a superset of p of y given x. P of y given x is, if you like, just a marginal over p of x and y. So unsupervised learning is solving not only for modeling a distribution, but for solving all of the marginals that lie within that joint distribution. And that's why it's not specific to any particular task. For instance, way back in 2021, I asked Lambda, one of the earlier large language models, to translate a sentence from Turkish into English. And it balked a little bit in the beginning and said, sorry, I'm not good at languages, but I insisted and forced it to, and it did. And this despite the fact that it hadn't been given any parallel corpora, with or supervision, right, in these two languages, but it did happen to have ingested Turkish Wikipedia along with English Wikipedia, so there, it did know Turkish, as well as knowing English, and it was able to do the translation because this is just one of those marginal distributions, if you like, that was embedded within that larger joint distribution. Short-term memory and self-consistency can be seen as just likelihood of the future given the past as well. If I ask a model like Lambda, what is your favorite island in the world? One might say, this is a stupid question. It has no favorite island in the world. But of course, given that the distribution that it's approximating is, a person, people generally will come up with, a favorite island. They won't just say, I don't have one or my favorite doesn't exist. So it'll come up with something, and there's something arbitrary about what it comes up with. But whatever it comes up with, it will then remain consistent with that. So it says, I really like the island of Crete. I say, do you prefer Lambda Island to Crete? No, I prefer Crete, as it is much bigger and more interesting, especially the Palace of Knossos. Of course it'll say that, because the likelihood of it changing its mind and saying, oh yeah, I prefer Lambda Island to Crete, is much lower than the probability of it doubling down on what its original preference was. So, if someone is sort of a non-believer, if you like, then they will say, well, this is a classic example of bullshitting. But there are a bunch of very interesting studies that have been done. They're detailed in a book called The Mind is Flat by Nick Chater that I found very provocative. He wrote it before this whole large language model era, I think back in 2017 or 2016. And he details studies in which psychologists do things like go up to people in the street and ask them about their preference. Which of these two faces do you find more attractive? Or which of these two jars of jelly do you prefer? And you get a taste test. Or which of these political opinions do you agree with? And people will answer. And then there'll be some distraction stuff, some other tasks. And then they'll be reintroduced to whatever they said earlier, except with the choices swapped. So, the researcher will say, so why did you find this person more attractive than that one? And it'll be the other way around. Or why did you, agree with this political position where the positions have been reversed? And the shock is that only about 30% of people notice that the reversal has occurred. But everybody immediately justifies the answer. And there's no difference in fluency or in consistency or whatever, of the explanation, no difference in detail. It's like your inner lawyer springs into action to retroactively predict, why it is that you made that choice. And even more alarming, if it was a political thing, then 6 months later in an election, they were likely to actually vote in a way consistent with whatever got flipped in the during the process. You can imagine this was quite an interesting result for political operatives. So, in other words, this idea that we have an inner self and that we are interrogating it when we get asked a question like that one, and that there's like a true answer, and and this is just a matter of looking or interrogating, is maybe a little less true than we would like to think. It's more like we are a story that we tell ourselves, and we begin telling that story in the moment when we need to. It's kind of a just-in-time sort of thing. And once it becomes part of the token sequence, if you like, part of the past, then we try and live our lives in the future consistent with that story, unless we make some deliberate attempt to change our story, if you like. So, it's a little bit of a pessimistic result in a way, but I think a very, very interesting one. I won't go through this theory of mind example, but theory of mind is, I think, a really profound instance of what intelligence entails, being able to put yourself in the place of others and imagine what they're feeling. In a sense, I think it's the root of all intelligence, because at least according to the social intelligence hypothesis that has been advanced by Robin Dunbar and colleagues, the reason we've got big brains is because our most important environment is each other. And it's very, very advantageous for you to be able to predict what somebody else is going to do or say in a given situation. It's also very advantageous for you to be able to predict what you yourself are going to say or do in a given situation. And those are actually the same task. So empathizing with yourself, if you like, is self-consciousness. And it's the same basic task as empathizing with others or predicting others. And they're both evolutionarily useful. You need to be able to empathize with yourself and to predict yourself in order to do any form of long-term planning. If I'm asked, like, do you want to take this red eye, next week to, give the talk in DC? I have to sort of cast myself forward and think about what my situation is going to be, in order to say yes or no. I said yes in this case. And likewise, if you're in the monkey troop and, you see like another monkey coming towards you and looking at your injured knee, in a certain way, like you really want to get inside that other monkey's head and understand like what's going to happen now, right? What's the situation going to be? And obviously the primate that does a better job of being able to do that sort of modeling is going to have advantages in all sorts of ways. These are stories that Frans de Waal has investigated in detail and a bunch of other primatologists. So anyway, that likely accounts, that social intelligence hypothesis, I think accounts quite well for why among primates and among cetaceans and in a few other lineages, basically the really intelligent animals on Earth, we've seen these kind of exponential growths in encephalization that over relatively short periods of time that seem to be driven by essentially modeling the conspecifics, modeling others of your own species, and the relative advantages of being able to do a better job of that, of doing better politics, if you like. There is an intriguing counter, or maybe it's an exception that proves the rule here, which is octopuses. I don't know why octopuses are intelligent, because they're not particularly social. They're sort of the exception. However, octopuses are also weird in that they have this very high degree of self-symmetry. And I have a sort of pet theory that maybe their arms are actually social with each other, and the reason they have this very decentralized nervous system is because they're actually little villages of 8, actually, each of them. But anyway, that's just my bullshit theory. All right, so what is missing from an LLM? Part of it is probably just more scale. Part of it is multimodality, although that is very, very rapidly changing as transformers start to give and take tokens of more and more kinds. Vision transformers combined with motor transformers combined with language transformers, etc. An inside voice is definitely part of what is missing. I think a lot of the problems that we see with transformers today when they get queried is that we're kind of forcing them to emit tokens as we turn the crank, and they have no internal state that's not visible to us. So, if they can come up with the answer to something immediately, then we see it. But anything that when we are asked ourselves, we have to actually think through, or there's any inner voice, there's any sort of back and forth in our own heads, is not going to work, right? In the current transformer context, because they can't talk to themselves. This is actually why chain of thought probably works, because it essentially gives the transformer the leeway to talk itself through a task, and thereby to to have a bunch of the processing happen in that space. We're able to actually see it, unlike with each other, unless we have, I don't know, serious Tourette's or something. Experimental or Montessori learning is something that today's transformers don't have either. The fact that they do learning separately from inference is not the way we operate, of course. And finally, ongoing continuous learning is required for things like an experimental or Montessori approach to life, which you learn from experience. And this whole question of what the gap is, what's the delta to ongoing or continuous learning is, I think, one of the most important areas of research into sequence models today. And sociality, of course, is the big meta thing here. Although I would argue that that's largely a matter of setting as opposed to of what's going on in the model itself. I mentioned audio LM in the multimodality vein, but I'm going to skip discussing that. I will mention that this inability to form new memories, the fact that there is a context window and that nothing that occurs outside of the context window gets remembered by the model, that the weights are all fixed, I'm certainly not trying to draw any equivalence between AIs and people, but the symptomology is a little bit reminiscent of what happened with Henry Molaison, HM, when his hippocampuses and entorhinal cortices were resected in a last-ditch and successful attempt to treat his intractable epilepsy in the mid 20th century. So he became, at that point, the most famous neuropsychiatric patient of all time because he had total anterograde amnesia from then on. So he had very coherent, cogent conversations, but if he became distracted, or a few minutes passed, you could have exactly the same conversation with him again. He didn't, and in many ways, right down to sort of the pauses, the digressions. It's quite disconcerting to watch videos of interviews with HM because you really see how much of our, if you like, inability to predict each other actually comes from the fact that we have memories and that we are taking pains not to be predictable. That we will never say the same thing twice. In conversation with somebody else because, in this social intelligence hypothesis, I guess there is something adversarial about this whole predictive game. You never want to be fully predicted by others, and we use our ability to form memories continuously to avoid prediction. Something which HM became unable to do when he had his brain surgery. So. There's a very, very interesting result that Johannes von Oswald and collaborators on my team published back in December of 2022 originally, and there's been some follow-up work since, called Transformers Learn in Context by Gradient Descent. I think this is an interesting result because it points to something pretty important about sequence learners vis-a-vis their generality as artificial general intelligences. There was a paper a long time ago, back in the early days of language models, maybe 3 years, that was entitled something like "Language Models Are Few-Shot Learners." And they were talking about the fact that you could prompt or specify, in the prompt, a few examples or even no examples of something novel, and it would appear as if the model learned from that with respect to anything that follows in the prompt. For instance, an example that Peter Norvig, just kind of whipped up for us a few weeks ago was you say to a language model, an equiantonym is a word with the same number of letters as another word, but that means its opposite. Give me some equiantonyms. In that case, that would be zero-shot learning because you're not even supplying any examples, although, few-shot learning works in this context too. And it's able to do that. Equiantonym, of course, doesn't exist. It's not a thing, right? This is an invention. So essentially, you are teaching the model something, and we know that few-shot learning in the usual gradient descent sort of way works with these models, and that it can be very efficient, given that they have an efficient representation pre-existing with language. But it seems to learn in real time from what is in the context window. What could that possibly mean, given that all the weights are remaining fixed? So it was always something that confused me, and Johannes shed a lot of light on this. And produced a plot that, for me, is one of the most interesting plots I've seen in the last couple of years. So what he showed was that you could take a very simplified sequence model with just one attention layer and sort of program the attention layer, so make a construction out of the attention layer that would actually perform one step of gradient descent on the contents of the context window and make the subsequent responses as if the model had taken a gradient step. And he furthermore showed that if you added layers, if you added attention layers, then for every attention layer you added, you could take an additional gradient step if the weights were set up just so. Now, if he had just made this construction, then I would have thought that's a fun result, but there's no evidence that that's what's actually going on. But in fact, there is evidence that that's what's going on. So this plot is a trained transformer with n attention layers as blue crosses. and n gradient descent steps as a green line. And you can see that the two curves are exactly coincident. So it really does look like the attention layers are performing this gradient calculation and literally doing something just like backprop in the forward prop. That's really cool because it means that pre-training is meta-learning. It means that when you train a sequence model on something like language, you're actually having it learn to learn as well as learning what was in the sequence. There's no difference between meta-learning and learning, and I think that's quite profound because this comes back to what are the fundamental functions of language. Language is a sequence that is designed to be able to teach new things in a compact way. Like when I say something like an equiantonym is blah blah blah, that's quite remarkable, right? That with just a few tokens, with just a few words, I'm able to express a novel compositional concept that you can then apply in a novel setting. It's not like I had to give you a lot of training examples, right? Those words were enough. And predicting the future, given the past of those tokens, involves learning the skill that those words expressed. So I think it's quite profound, and it means that really all we've got to do now is figure out how to take that learning that happens in real time and bake it back into some subset of the weights, and we've got a hippocampus. And I think that's probably the single biggest gap between today's LLMs and something more like what we've got between our ears. Now, in the last, I have a few minutes left, I hope. So I want to talk. Yes, do I have a few minutes left? Good. Okay. So I'd like to now take a giant step back and talk a little bit about the deep origins of prediction in evolutionary biology, and I really mean deep origins. So this is a black smoker on the seabed, and Nick Lane and others believe that these are likely the places where life began on Earth, the sites of abiogenesis. According to Lane's theory, which strikes me as very plausible, before we had RNA or DNA or anything like this, we had metabolism. And metabolism arose in places like this because these are places where there is hydrogen gas and carbon dioxide bubbling up out of the core of the Earth through these very friable rock chambers that are full of thin rock walls where natural proton gradients begin to occur across the rock wall. And when you have this proton gradient, an energy source, and you have carbon dioxide, and you have ferrous chemicals in the walls of the rock, which can serve as catalysts, you have all the ingredients you need in order to start up a cycle of chemical reactions that look a whole lot like the reverse Krebs cycle, which is the metabolic loop at the core of some of the most primitive anaerobic bacteria that synthesize all of the carbon skeletons of everything that we use in our cells, including DNA and RNA and lipid membranes and proteins and everything else, out of nothing but carbon dioxide and proton gradients and water. The Krebs cycle in our own cells is actually that same thing running in reverse, which requires an input of energy from it requires burning oxygen. But the reverse one is the one that actually does biosynthesis of all of those molecules that we ultimately rely on. So anyway, thinking about how those loops began, is sort of an interesting thought exercise because it seems like the kind of violation of the second law of thermodynamics that characterizes why life is so weird. Normally things get simpler over time, right, left to their own devices, and this is a situation in which simpler stuff gets more complex. It's sort of you drive up the gradient of complexity rather than down. How does that work? So. There's a chemist now retired, I think at Hebrew University, Adi Pross, who's written about this in a book called What is Life? Same name as the book of Schrodinger's from the middle of the 20th century. And Adi Pross's idea is that this is really about dynamic kinetic stability, meaning that there are autocatalytic loops of chemical reactions that are actually more stable than the static stability sort of situation where everything just settles to a ground state and is static. This dynamic stability is more stable in the same sense that DNA is a more stable molecule than granite. Granite obviously is very robust, but it doesn't repair itself. It's not anti-fragile, it's just robust. Whereas DNA continuously reproduces itself, and this loop, this dynamical loop, turns out to be more durable than something that just stays put. So I began doing some simulations with a system that I call BFF for reasons that I can explain a little bit. But these are little strings of programs. So they start off as strings of 64 characters that represent a program in a programming language called brainfuck. Which was designed in the 90s by a smart-ass German computer scientist, not my name. But it's a very, very simple Turing-complete programming language of only 8 or so operators that nonetheless you can express any program in. And what I did here was to just take a soup of these programs of length 64 and put them in a pot and apply some heat, which is to say random mutation. So they start off as random strings, they don't do anything. And just take a pair of them, stick them from end to end, and execute. It's self-modifying, so they can if the program does anything, it can read and write to itself. So it does whatever it does, and then I take the parts back apart and dump them back in the soup and repeat, and that's it. That's all that's happening here. So starting from nothing but noise, you get life, basically. You get dynamic kinetic stability. You can see that. So here are some screenshots of, in the beginning, there are only 2 operations per interaction because out of the 64 bytes, or 64 random bytes, there are only likely to be a couple of bytes in any given program that even code for anything, that are even operations at all. So, 1 million interactions in, nothing has happened. 2 million, nothing. 3 million, nothing. 4 million, nothing. And then at 5 million, there's this phase transition to something that looks an awful lot like life. Or metabolic loops, if you like, in which each of these programs is catalyzing reactions with other programs that lead to reproduction of themselves in some way through some loop of intermediates. There's quite a beautiful way of visualizing this phase transition. This is the number of interactions on the x-axis, and there are 10 million dots on this plot. Each dot is one interaction, and its y position is the number of operations that took place in that run. And what you can see is that something really quite magical happens, and the amount of computation suddenly increases dramatically at 6 million. Here's a nicer way of visualizing it. That's the Kolmogorov complexity of the soup. So the Kolmogorov complexity is just the compressed size. In the beginning, it's 1 because it's random noise and it's incompressible. But at the phase transition, the complexity drops dramatically because suddenly there's all of this structure. So this is DKS happening. There is a way of formulating DKS, or dynamic kinetic stability, that makes it clear that what is really going on is that if you think about all those molecules as actors, right, they're computational actors, and they're basically predicting the future. They're autoregressive agents. And if they successfully predict their own future, they will survive. If you think about it, like the reason that a bacterium with chemotaxis, works and is still alive after billions of years is because all of the generations of bacteria with chemotaxis successfully predicted their own survival and acted in accordance with that. That is, they emitted tokens that brought about the conditions for their own survival later on. And that's exactly what these molecules are doing as well. So, there's a sense in which I think we're kind of living atop a stack of systems that are basically all doing the same thing. They're all just predictors, ranging from molecules and perhaps even lower down, all the way up to us, and in fact now including AI as well, all doing the same thing. Each step that you take gives you a more powerful computational platform for doing higher order prediction and more efficiently, because with every one of those reductions with every one of those kind of constraints, if you like, wherein the computation happens in a more bounded statistical space, the ability to learn is accelerated. So I think I'll stop there if we have any time for questions.
Let's take a seat. Here's your mic. Make sure it's switch it on here. So, wow, we've heard quite a lot now. And yeah, I can already see the first questions coming up. Yeah, Mayank.
I'm Mayank from UCLA. So this talk, very interesting. You covered a lot of topics from bacteria to phase transitions, intelligence. But lots of questions there, but maybe I restrict myself to just one. So you mentioned hippocampus, and we've been working on it for many years. We found predictive coding in just a perceptron. So the question for you is, and it's a bit of a loaded question, but I think you can answer that. Do you think human infants who can't speak are intelligent? Is there any core of intelligence in human infants? And second thing is, if I imagine the answer would be yes, then is there intelligence in a chimpanzee or other ape? And how come, even though they reach much larger amount of training, so-called growing up in multimodal natural environment, they don't exceed human infants' ability beyond 4 years? So what do you think in terms of AI? Can AI reveal to us something about that?
Yeah, that's a great question. I think so. And I think that, yes, I absolutely think that chimpanzees and bonobos and so on are intelligent. And I think they're intelligent in exactly the same way that we are. The difference lies really in two things. One of them is that our assessment of intelligence has the same kind of nonlinearities in it that the researchers I mentioned talked about in their mirage of emergence sort of thing, right? We also are very nonlinear about this. When we look at all the things chimpanzees can do, and we say, but they can't do calculus. That's sort of that last step, if you like. That is maybe not that much more complex than all the things that they do, but that we, because of our human exceptionalism, we decide that that's the threshold. But also, I think there's a deeper answer too, which is that we are the only eusocial primate. So, we have language, and this is a really big deal because it also gives us anonymous societies in which we can band together in groups much larger than the few dozen that are the sort of maximal size for a chimpanzee troop or a bonobo troop, and because our intelligence, I believe, is not really just an individual property. So the scaling laws are not just about how many neurons are in our brains, but about how many people in the society. There's been a lot of very beautiful study of scaling laws of technology and of language and of various other things as a function of number of people in a society. You see, places like Tasmania, when they got cut off from the mainland, their level of technology dropped quite a lot, for instance. Same with linguistic complexity effects in islanding. So I think that when you start to realize that technology is also a group property, and that much of our environment is each other, and therefore the scale of how many others we can benefit from is a huge factor. I think a lot of the mystery goes away in the difference between us and chimps.
But large language models may not be able to capture it because grown-up chimpanzees or an infant doesn't have much of a language. So what kind of AI might we need which will capture the intelligence that is not expressed in terms of language?
Well, there have been a slew of papers in the last year that show that sensory maps of all kinds, in fact, all of the known human senses, are actually rendered in language to a degree that you can kind of recover sensory maps from pure language-based LLMs. That's really interesting too, and it's not something that I would have predicted personally. But the fact that we use language to talk about all of our experiences and all of our senses means that all of that knowledge is latent in language. Of course, we also are starting to have sequence models that have multimodal inputs and outputs as well, so they don't have to rely only on language.
Thank you.
Thank you.
So, audience first, please.
It's just a question that is related with the precedent one about the monkeys. So when you were asking about the language of the monkey, I think it's possible to transcript it in a telepathical way, because I think animals also have telepathy. It is the most universal language, and humans also has it. So it's not a language like with the words that human knows, but did they try to see the telepathy with the monkeys?
Well, I don't know whether you mean telepathy metaphorically or literally.
Do you know what is telepathy, generally?
I do.
So this is the same. definition for the animals that are used.
Okay.
So did they try this solution?
I mean, we do. There are a lot of studies that underway to study languages in animals. Including using sequence models. This is happening with sperm whales and orcas, for instance, and also with primates. And we know that animals, of course, communicate. Some of them have quite rich forms of communication with each other. Orcas even have local languages. A given pod will have its own cultural evolution too. But if what you mean by telepathy is something supernatural, then I don't believe in it.
For example, when I mean telepathy, it's just like, let's say, projection of images, imagination, right? We all have this, and animals, they have also. So did they try this method of how to read the mind projection of the animals, that is just pictures?
Again, I guess I'm not really sure how literally to take you. I think there have been a lot of studies that debunk literal ideas of telepathy in humans, but there is a sense in which language itself is telepathy. And of course, when we look at nonverbal, I mean, we saw an example with Aldo's talk of even just looking at the movement of the body, right? There's a lot communicated emotionally there as well. So there are many cues that let us put ourselves in the minds of others, and I do think that putting ourselves in the minds of others is fundamental to intelligence, I mean, as I've said. But I do want to be very clear that I don't think any of that is supernatural. I think that that's about it's about our sensory inputs and our ability to make inferences.
Okay. I do have a second question. What do you think about the brain chip trial actual of Elon Musk?
About the sorry?
I'm talking about the brain chip, I don't know.
Brain chips.
Okay. Elon Musk, he had the patent this year to make on human trial. Mm-hmm. So what do you think about this?
I think that the natural inputs and outputs that most of us have with vision and audition are much higher bandwidth than any brain-machine interface that we've yet devised. So in that sense, I mean, I think brain-machine interfaces are really interesting, of the kind that Dan was talking about earlier, as prosthetics. But I guess at this point I'm quite skeptical that they are going to exceed, at least in any way that we would want to use them, among the able-bodied. I think they're not going to exceed easily the natural I/O ports that most of us are born with.
Thank you.
Thank you.
There's more. Yeah.
Hey, loved the presentation. Just had a quick question for you. You talked about, the older just predictive text and texting, and how it's almost like that plus attention to an extreme for what we now have with like the large language models, learning models. And I'm just curious, like, what do you see as the main constraints from basically for AI to get more intelligent? Is it just more data? I don't know. Would love your thoughts there.
Yeah, I don't think it's more data. I think that we have enough, and to the extent, and in some sense, the amount of data being used now, is sort of, it's far in excess of what we grow up with. And a lot of that is because of the inefficiency of the pre-training stage. So I think computational constraints are the biggest thing right now. We're still doing computation using the same kind of Turing von Neumann computing architecture, that we invented in the 40s. And that was invented in a time when the individual components, when the switches, were very, very unreliable and expensive. It's vacuum tubes. And so the whole point of having a separate processor and memory and a bus connecting the two was to minimize the number of switches. Now, and of course, all of that all benefited from Moore's law as the processor got faster and faster, and we had bigger and bigger programs. But neural computation is fundamentally really different from classical computation. There isn't a program, and everything proceeds in parallel. So I think that our biggest bottleneck is actually reinventing our computing base to be more like the way brains actually work. And we obviously have a lot of headroom there because we have great examples of 20-watt, highly parallel trillions of weights processors, between our ears, right? So, and using methods that I think are frankly quite janky. So I'm sure that it's possible to do a lot better without any fundamental advances in technology, and I think that's the biggest constraint.
Gotcha. Thank you.
Stephanie, do we have something from our audience far away?
It says, what are your thoughts about the recent LLM GPT-4 capabilities, specifically how they can interpret thoughts and images using MRI scans?
Yeah, so this also, I think, came up in some of the earlier talks. Again, Dan's comes to mind. The idea that we used to think that the brain was a bunch of specialized parts, and in a way this was part of the Chomsky belief too, that we had a language organ that was specifically that was very, very specific to language, and that had a bunch of slots that were filled by whatever specific language you learned, and vision presumably would be a whole very specialized system in its own right. And I think we began to see cracks in that narrative, even back in with these old experiments from decades back, in which you take a fetal rat and you rewire say its visual, its optic nerve into its auditory cortex, and it still learns how to see. All of that suggests a much, much more general algorithm or circuit, if you like. And I think if we imagine that circuit is prediction, across multiple timescales, that does go a very, very long way toward explaining things, which is why that alone, plus wiring constraints, give you such a good picture of retinotopic maps and other kinds of patterns that we see in cortex. So I think a lot of those patterns that we see in cortex fundamentally just have to do with the structure of experience of the data, and that's why they're so easy to reconstruct from large language models.
Right. There are two questions, I believe, but I know we're kind of going on time. Is it okay to continue?
Yes, we've got a little bit more.
What do you think about the opinions of Yuval Harari on AI?
Well, I haven't really followed the details of what Harari has been writing about AI recently. I think he's a bit of a scaredy cat about it. Am I right about this? I hesitate to say things because I think so much has happened in the past year, and I haven't followed what he has said about this in the past year.
Okay. This is kind of a three-part question, so I'll read it out, and I can repeat as needed. Currently, we have a serious gap in our knowledge of living brains. We lack an understanding of the brain structure and dynamics. Secondly, current technology does not enable us to capture all the information processed by a living brain. Thirdly, each brain is unique, so we need to explore them statistically. That said, how can we replicate such a complex system without that knowledge?
Yeah, it's a great question. There have been efforts for years, and there are always new ones, happening. Of let's try and reproduce mechanistically what brains are doing. The ill-fated Blue Brain project, of Henry Markram et al. Was one of those, and there are more modern, more sensible versions of it as well. But I think there are really two very different philosophies that one could take to thinking about what brains do. One of them is very mechanistic. And when you begin with something very mechanistic, you are going to be really hobbled by any gap in your understanding of the details of what is going on. We know that a huge number of the proteins in the human genome are used in neurons. There's a huge number of neuron-involved signaling mechanisms, most of which are not understood. So I'm very skeptical of attempts to model the sort of mechanistic details of how brains work from the bottom up until we have understood a whole lot more about how brains work. So in that sense, I fully agree. On the other hand, I think it is also really remarkable that intelligence, in all of the senses that we think about it today, has evolved over such a short time, over so few generations in the evolutionary record. And I kind of think the reason is that the basic recipe, what it's doing at a more abstract level is actually quite simple. And doesn't depend on all of those mechanistic details. That is to say, the mechanistic details are important for the implementation, but they maybe are not central to the what, if that makes sense. If the what is sequence prediction, then doing sequence prediction another way will yield very, very similar results, which is, and I think that things like the reproduction of topographic maps or fMRI maps, Jack Gallen has done some of this kind of work of how, sort of word clouds look like they map pretty precisely onto LLM embedding spaces. All of that is evidence for the idea that a lot of the things that we have imagined are complicated and programmed are actually emergent phenomena that just come from prediction and learning in a very generic way. And again, Dan's results that he showed earlier today, I think, are also good evidence for that.
Okay, great. Those are all the questions that came virtually.
Yeah, thank you very much. And thank you, Blaise. We could go on for hours. You triggered so many questions, but we may continue afterwards. But now, first, let's give him a round of applause.